Consider the cationic polymerization of isobutylene using SnCl4 as the coinitiator and water as the initiator. Under certain conditions, the polymerization rate was found to be first order in SnCl4, first order in water, and second order in isobutylene. The number average molecular weight of the initially formed polymer is 20,000. A 1.00 gram sample of the polymer contains 3.0 times 10 to the negative 5 moles of OH groups. It does not contain chlorine. Show the reaction sequence of initiation, propagation, and termination steps for this polymerization and derive the appropriate expressions for the rate and degree of polymerization. Indicate clearly any assumptions made in the derivations. Since we know the mass of the polymer, which is 1.00 grams, and we know the number average molecular weight of the polymer, which is 20,000, we can find out the moles of the N groups, the number of moles of the N groups. So mass of the polymer over the number average molecular weight gives us the moles of the N groups. So 1.00 divided by 20,000 is 5 times 10 to the negative 5 moles. So this is the number of moles of the N groups. And we know that 3.0 times 10 to the negative moles, 5 moles of OH groups are present, which means 5.0 times 10 to the negative 5 minus 3.0 times 10 to the negative 5 is 2.0 times of 10 to the negative 5 moles of N groups other than OH are present. Also, we know that it does not contain chlorine. So we can assume that the 2.0 times 10 to the negative 5 moles of N groups are coming from the C double bond C resulting from chain transfer to monomer. So this is isobutylene, and when this polymerizes, we get this as the monomer repeating unit, and during chain transfer to monomer, will get terminated like this. The equation for initiator co-initiator of stannic chloride and water would be SnCl4 plus water, and this would be equilibrium reaction giving SnCl4 hydrated with water. So let its equilibrium constant be K. Equilibrium constant K can be written as SnCl4 dot water concentration over SnCl4 concentration times concentration of water. Since it's difficult to determine the concentration of this, we can write this in terms of K to say that concentration of SnCl4 dot water equals K times concentration of SnCl4 times concentration of water, and we can plug this into the rate of initiation. The propagation step would be HM plus SnCl4 OH minus N times is reacting with a monomer to give HM N plus 1 SnCl4 OH minus. This would be Kp. This is a termination step with chain transfer to monomer with rate constant Ktr. Termination step, which gives rise to OH groups, we can say that this would be the equation where HMnOH is formed plus SnCl4. And since there is no chain containing chlorine, these are the two termination steps: transfer to monomer and formation of OH group in the polymer. Now let us write the rate of initiation. Rate of initiation is going to be based on this equation. So rate of initiation is going to be Ri equals Ki times the concentration of this. So concentration of SnCl4 times concentration of water times concentration of monomer. Similarly, we can write the equations for rate of propagation and rate of termination. Rate of polymerization equal to rate of initiation times rate of propagation over rate of termination. So this would be Ki K Kp over Kt times SnCl4 times water times monomer concentration. There has to be a monomer concentration here. So if you come back, so it will be monomer concentration squared. If let's include this SnCl4 OH minus over HMN plus SnCl4 OH minus, and that's going to get cancelled. Okay, so this is what we'll be left with. So we'll be left with rate of polymerization is equal to Ki K Kp over Kt times concentration of the initiator and co-initiator times monomer concentration squared. Now degree of polymerization can be given as rate of propagation over rate of termination. So we include both the kinds of termination, transfer to monomer and the one that forms the OH group, which is equal to Kp times HMN plus SnCl4OH minus times monomer concentration over RT, which is Kt times HMN plus SnCl4OH minus plus KTR times HMN plus Cl4OH minus times monomer concentration. So this gets cancelled. We get Kp times monomer over Kt plus KTR times monomer. So this we get from this equation. Okay. So we have the monomer here, and so we had to include the monomer concentration. We can consider another scenario in which SnCl4 reacts with water in a slow reaction with rate constant K, giving SnCl4 dot water. So the rate of initiation will be K times SnCl4 times concentration of water. This would react with the monomer in a fast reaction to do the initiation. And then if monomer solvates the propagating center, then rate of propagation would be Kp times concentration of this times the monomer concentration squared. Because we'll have HM plus SnCl4 OH minus plus M plus M, doing the propagation reaction to give you HMN plus SnCl4 OH minus. So we got the rate of propagation. So if we combine these, with the rate of termination that we already got, which is Kt times HMN plus SnCl4 OH minus. To get the rate of polymerization, we can say that it's equal to rate of initiation, which is K times concentration of SnCl4 times concentration of water, and then times Kp times concentration of Hm plus SnCl4 OH minus times monomer concentration square over Kt, which is times Hm n plus SnCl4 times this can be written as Mn plus here, so Sn minus times M, and that will give us, these two get cancelled, so the rate of polymerization is equal to Kp over Kt times SnCl4 times water times M squared. So this would be the case if the initiator co-initiator is not an equilibrium reaction and it's a slow reaction, and the propagating center is solvated by the monomer.